Hey guys, so today we're going to be talking about Le Chatelier's principle. Now, I'm back on the headphones because there's something going on with my other mic, so yeah, I look like I'm about to go fly a plane or do something ridiculous, but it is what it is. So let's get started. So Le Chatelier's principle is based on the work of Henri Le Chatelier. He was a really influential French chemist of the 19th century. He lived from 1850 to 1936, and he really examined um, the way that pressures on a system or shifts in a system would influence the chemical outcomes of that system. So we're going to be looking at all of that today. So let's kind of approach Le Chatelier's principle through the lens of equilibrium. Okay? And I'm going to use an example that's going to sound a little bit weird, but go with me on it. Imagine you are a chicken farmer. Now, there are some things you need to know about chickens. Number one, chickens can't sweat. Did you know this? Like, we get too hot, we sweat. Chickens can't sweat. They don't have sweat glands. So if a chicken in its chicken coop or wherever it happens to be gets too hot, they pant like a dog or a cat does. So this influences a very important reaction that happens inside the chicken. Okay? So chickens need CO2 or carbon dioxide to go together with calcium oxide to form calcium carbonate. The calcium oxide is provided in some way in their food. The CO2 is in their breath, and this calcium carbonate, the end product, is actually used to make the shells of the eggs. So if we're chicken farmers, and we're chicken farmers not because we're selling chicken meat, but because we're selling eggs, and we have our chickens, and it's summertime, and the temperature starts heating up, the chickens are going to pant more. If they pant more, they're giving off more CO2. And this stresses the system and shifts our equilibrium to the left. Now, because it's shifting to the left, which I guess to you guys looks like that, and away from the end product or the eggshells, this makes the eggshells thin. Now, that might not seem like a huge problem, but if you're a chicken farmer and you're selling eggs, you really don't want thin eggshells because when the chickens sit on their eggs, then they break them, which is no good. So what can we do? So remember our equation. We have calcium oxide from the food, calcium dioxide from their breath, making the calcium carbonate for their eggshells. So in the summer, the carbon dioxide in the chicken's blood goes down because they're panting. Okay, so how can we counteract this? All right, we want to keep the equation from shifting to the left. We want the eggshells to stay nice and thick so that chickens don't break their eggs. So how can we increase chicken eggshell thickness in the summer? Take a moment, think, and tell me of a way we might be able to do this. No harm, no foul. Want you to try. Alrighty, so some of you might have said air condition the chicken house. Well, I'm sorry. We're chicken farmers and we're not made of money, so we're not going to be doing that. It costs too much money. Some of you might have said, well, pump carbon dioxide gas into the chicken house. Get more carbon dioxide in there for the chickens, right? But no. What's a big problem if we do that? That's right. You are going to suffocate all your chickens. You're going to kill them all. And that's not a good look. So what else could we do? Well, we could give the chickens carbonated water, seltzer water. This would get more CO2 into their little bodies, and it wouldn't be suffocating them. That could be a good option. If we did that, that would shift our equilibrium toward the calcium carbonate, toward the eggshells, because we're giving it more CO2 as a reactant, so then it can make more product. So that could work. Well, what if we put calcium oxide in their food. Well, this also increases the reactants and allows us to move more vigorously toward our products. So that would also shift our reaction to the right. It would shift us toward the calcium carbonate. So this is the idea behind Le Chatelier's principle. It's the idea that if we make a change in a system, that system will then shift direction in order to compensate for the change that we made. You saw this in the equilibrium game. And we're going to have you go back and do some additional levels of that so that you can really see this in action. Now, for the purpose of all my examples going forward in this lesson, I am going to use the Haber process equation, where we have nitrogen gas, hydrogen gas reacting together to produce gaseous ammonia and heat. And this is a reversible process. We can take that ammonia, we can add heat to it and push it back into making nitrogen gas and hydrogen gas. It's really important for us to note in this reaction that everything we are using is in gas phase, okay? And that's going to be super important to us as we go through. So let's take a look at our first idea. So how can we remember what happens in our shifts really easily? Well, anytime we add something, the reversible reaction is going to want to shift away from the thing we added. So if we increase one side, the system's going to want to shift and increase the other side to match it. All right? On the other hand, if we take something away, we're going to move towards that thing we took away. So if we take something away on one side, the system is going to shift toward the thing we took away to try to replace what we removed. Okay, so add, away, take away, towards. I think that'll help you remember what we're going to be doing. So let's look at example 1. In which direction, helps if I can talk, will our reaction shift if you increase or add these things? So what's going to happen? Let's start with our nitrogen. What's going to happen if we increase our nitrogen? Well, we've just increased on our reactant side, and that means we're going to shift to the right. We're going to be shifting away from the thing we added. All right, so I'm going to erase those marks. Let's look at our second one. So if I add hydrogen, which way am I going to shift? I want you to try to answer this one before I do. All right, if I add hydrogen, I'm going to shift to the right because I'm going to move away from the hydrogen, and that's going to let me make more products to balance out the increase in the reactants that I just made. Alrighty. What is going to happen if we add ammonia? Try this one. So if we add ammonia, that's on what we traditionally think of as our product side, which means we are going to shift left. Because if we add product, that means we're going to go back, we're going to make more reactant. We're going to shift away from the thing that we added. And all of these we're asking about adding. Great. Let's go to our next example. So in example 2, which direction will this reaction shift if we decrease or take away the concentration of the following things? Alrighty, so you tell me what's going to happen to our system if we decrease the nitrogen. So if we decrease our nitrogen, when we take something away, we move towards it. So that means that we are going to move to the left because the system is going to want to replace the nitrogen that we just took away. All right. Now, what is going to happen if we decrease our hydrogen? So if we decrease our hydrogen, we are also going to shift to the left because the system is going to want to replace the hydrogen that we just took away. And lastly, what's going to happen on the other side? What's going to happen if we decrease the ammonia? What's going to happen to our system? Which way will it shift? So if I take away ammonia, my system is going to shift to the right. And that's because the system's going to try to replace the ammonia that I took away. All right, so remember, add, away, take away, towards. Let's look at some more examples. So what happens when we start playing with the temperature? Temperature has an effect as well because reactions are either endothermic or they're exothermic. So if a reaction is endothermic, meaning we're putting heat in the reactant side, adding heat will shift it to the opposite side. But if it's exothermic, which means we've got heat in the product side, adding heat will also shift it to the opposite side. And let's look at that in action. We're still add, away, take away, towards. So if I increase the heat in this equation, which direction will my reaction shift? Give it a try. No harm, no foul. So if I increase the heat, I'm adding heat. That means my system is going to shift away from the heat, which means it's going to shift to the left. And we're going to make more of everything on the left because we added heat. So the answer to this question would be we would shift left. Now, what's going to happen to our reaction if we take away heat or shift so that we are compensating for an absence of heat? So if we take away heat, this rule is still take away towards. We're going to shift to the right because the system is going to try to make more heat to replace what we removed, which means everything on the right will increase because we're going to shift to the right. And you saw this in the equilibrium game. I know that you did. Now, what happens with pressure? Well, pressure has its own rule. In pressure, we're not taking anything away or adding anything to the system. When we have pressure, it's really about the amount of moles of stuff. So pressure will only apply to gaseous systems. And this is why I pointed out everything we were using was a gas earlier today. So if we increase our pressure, our equilibrium is going to shift to the side that has less moles of stuff. So let's look at that in action. And if you decrease the pressure, the equilibrium is going to shift toward the side with more moles of stuff in it. So, in example 5, in which direction will our reaction shift if we increase the pressure? All right, so let's take a look at how many moles of our substances we have, because it's all about that. So we're increasing the pressure, right? On this side, I've got 4 moles of substance, because I have 1 mole here, plus 3 gives me 4. Here, I've only got 2 moles of substance. The heat doesn't count as matter, it's its own thing. So here we have 2 moles. So if I increase my pressure, I'm going to move toward the side with fewer moles, which means I'm going to shift right. Okay? Let's look at the next question. In which direction will the above reaction shift if I reduce the pressure? So once again, on the left I have 4 moles, on the right I have 2 moles. So if I reduce the pressure, I'm going to move to where there's more stuff. So that means I will shift left. Pressure always favors the side or wants to move toward where there is less stuff if we increase it, or where there is more stuff if we decrease it. Alrighty. So what happens when we add a catalyst? Well, we know that catalysts speed up reactions, but a catalyst will have absolutely no effect here because it causes both the forward and the backward reaction to go faster at the same rate. So adding a catalyst will not make an equation shift one way or the other. It's only going to make what it would already do happen a little faster. So let's summarize Le Chatelier's principle. So when a system's equilibrium is disturbed, it shifts to a new equilibrium to counteract the disturbance. So here, let's go through our possible disturbances. If I add more N2, what will happen? It's going to shift right. What about if I add more H2? It's going to shift right. What if I add more ammonia or NH3? It's going to shift left. What if I remove NH3? It's going to shift right. What if I add a catalyst? Well, there will be no shift because of the catalyst. What if I increase the pressure? It's going to shift right. Alrighty, so that's Le Chatelier's principle. It's all about establishing a new equilibrium after you have upset the equilibrium somehow.